Thank you. I'm going to jump right in, hoping I can get done with most of my talk. So much of this colloquium has focused on biomedical research that holds immediate hope of translation into application, whether a drug helps cure a particular form of cancer, for example. The issues of reproducibility in arenas like that are similar in some ways to those in exploratory science, but different in others. And I'm going to focus my remarks on exploratory science. Now, of course, exploratory science always precedes the more focused translational and clinical studies we've been talking about most of the time. But, and of course, a lot of biomedical research is exploratory, so my remarks are still quite relevant to everything we've been discussing. I'm not sure. Okay. There's general agreement that there are too many publications that report results, theories, and conclusions that are not reproducible. The implication is that too many are invalid, or that the effects or conclusions drawn from them are inflated or too small to matter. Thus, remedies for the way we practice science are called for. But these remedies should certainly do more good than harm, so we have to be careful how we apply them. The inflammatory rhetoric that we've often heard about reproducibility, in fact, even the term crisis, give the impression that science is failing and drastic remedies are required. But in fact, science is progressing rapidly in most spheres, producing new discoveries, results, explanations, and findings of benefit to society in ever more rapid progression, to the point where it's hard for most of us to keep up other than in our own very narrow areas of expertise. And that's a bit of a paradox, given the problems that we've been hearing about over the last several days, giving the impression that science is failing badly. How is it that we're proceeding so rapidly? I think it's due to the scientific social networks among leading scientists. And how this happens is a subject for another colloquium, not this one. The conclusion I'm going to try to emphasize is there are no magic bullet remedies based on some universal rule with general applicability. These remedies should be guides to good practice, but their application requires good scientific judgment. I'll try to be making this case. Okay, so any changes in the way we practice science need to be tailored to the goals of science. Now, there are 4 goals, I think, that are particularly relevant for the present issues. Optimizing scientific progress, understanding a substantive domain, maintaining and improving the reputation of science, translating basic science into applications that benefit society. And some remedies might help one of these and hurt another. So a remedy might slow scientific progress but improve the reputation of science. Or a company trying to translate a result into a profit-making application want to be far more certain a result is valid than would be useful for fostering progress in science. Reproducibility, we've been talking about, is obviously important. There are good reasons why concentrating on improving reproducibility in exploratory science might not be the best and most important way to accomplish the various goals of science. So, to take an example, discussions of reproducibility refer most of the time to reproducing a single effect or a data statistic. We should note that such demonstrations can be useful, but are hardly the best way to foster scientific progress. We learn much more when we study multiple conditions, establishing an overall pattern of results, even when each condition could be viewed as underpowered when they're considered alone. Those of us who build models to understand the processes at work in various scientific domains almost never model one effect or one statistic for obvious reasons. Too many models are available to explain any one finding. But we build models to explain a system of findings across a whole variety of conditions. I'm going the wrong way in my notes here. Okay, this colloquium is aimed at reproducibility, so I'll focus on my remarks the rest of the time on remedies for reproducibility, or for non-reproducibility. Should we concentrate primarily on eliminating invalid findings? An example, we could demand for a publication that the results be based on very large amounts of data with very large power, based on several studies representing variations of the experimental paradigm, and carried out by several independent groups at different sites where the experimenters have different beliefs about the existence of the effect. Most results wouldn't survive such a gauntlet, but those that did would be likely to be reproducible. Of course, that would eliminate most valuable studies in science and would slow scientific progress to a crawl. So we have to be careful about remedies that we apply. A certain proportion of invalid publications is an inevitable consequence of doing science well. And why is that? Science is a difficult and complex enterprise. There's a lot of inherent noise and uncertainty hindering our exploration of what is likely an infinitely complex universe. And that exploration is a noisy and a messy process. False leads are inevitable. Science corrects these or sometimes just bypasses them as scientific exploration proceeds. There's many factors involved in good scientific practice that cause non-reproducible results. So let me start with factors that produce a regression toward the mean, or a kind of one, a tendency for the second study to show smaller effects than the first. Much of science is exploratory, and scientists usually carry out several versions of their studies, refining the design and conditions, adding or changing control conditions, fixing errors, choosing design parameters that highlight most clearly the results of interest. These alterations are based on examination of the preliminary results, and these results that are observed help eliminate mistakes, help gain insights that guide better designs and conditions. The process of refinement continues until some optimum is reached. The early studies in this process are often useless, and when this is the case, of course, they should not be published. Of course, scientists wait until they get things right before publishing. But this process of refining studies can't go on indefinitely. It could, but it can't. The scientist has to choose when to stop and publish. The stopping point, almost always, is going to be when the results look good and when the implications appear clear. Using the stopping rule, therefore, causes the reported results to be accidentally better than would have been the case in an average version of the same study. It produces a statistical bias to have a strong result. Okay? Then an attempt at an exact replication, it's never possible to exactly replicate, but an attempt at an exact replication, therefore, tends to show smaller results for statistical reasons. In addition, we stop when the design most clearly demonstrates the desired result. But that means the design is well tuned to the local environment, the local context and the setting. A new study is almost always in a new context or a new setting, and the tuning to the previous setting, therefore, is no longer optimal in the next one, and we can again expect a smaller effect. That is, we expect a certain lack of generalization across study contexts. So, an appropriate scientific stopping rule prior to publication takes advantage of both statistical noise and design optimization, and as a result, effect size tends to be less in subsequent studies. Thus, when we see what appears to be a failure to reproduce, like in many of these studies of 100 studies or whatever, the smaller effect size could be a normal part of the scientific process rather than a sign of bad practice. Some large-scale replication studies have been interpreted quite differently by different observers, and in good part, this is the reason. Okay, I did say that stopping when the results are clear takes advantage of statistical variation. Now, that's not an excuse to collect too little data when it's easy to collect more. But generally, a major cause of the inability to reproduce is too little data or too little power. And the obvious remedy is to demand more data. There's a lot of remedies of this sort. Of course, we are beginning to realize that we should demand more power for publication than the null hypothesis criterion of 0.05. I like to substitute a much stronger criterion, preferably in a Bayesian analysis, but I don't want to get into the technical issues related to this. But on the other hand, too little data is often the result of factors that limit the experimenter's control. The difficulty of collecting evidence often forces publication of underpowered results. A case in point is many health publications. Investigation of a given disease syndrome, especially if it's a rare one, may have highly limited access to patients. One would not want to stop such studies because patients are hard to obtain. And having carried out the study, one should not decide to stop publication because the power is low. That would be unethical and would prevent progress in dealing with the disease. Now, that's just one example, but there's a wide range of situations in every domain of science where it's difficult to obtain data. And therefore, one has to balance the costs of collecting data against the need to have good statistical power. A fairly common reason for difficulty in obtaining data is cost, money and time. Cost of research is a problem we all face. All research requires monetary resources. Some are extremely large. Examples like this are found in every field of science, from astronomy, physics, chemistry, biology, and computer science through the social sciences and health sciences. And another cost is time. If data can be only collected slowly, an astronomer may have to decide whether to wait for the next supernova. Again, this is an audience that doesn't require examples, but again, balance is needed, the amount of data versus the costs of research. So I doubt anyone would think it's a good idea to prevent publication of promising data, promising research that's based on less than an ideal amount of data when the cost of research or other factors limit the ability to collect more. That would slow scientific progress. Obviously, it seems to make sense to publish promising results that will spawn new research investigations, possibly in less costly paradigms. So the bottom line is we should demand a high criterion for power whenever possible, unless a good case can be made for exception. We have to use good judgment. What should be the criterion for when we stop collecting data? Well, I prefer the Bayesian utilitarian approach, stopping data collection when an amount of evidence is reached that determines the effect size to a level of accuracy that allows one to draw meaningful conclusions. This kind of stopping rule is fine in a Bayesian approach, not in a statistical hypothesis testing approach. Sometimes the meaningful conclusion will be the existence of an effect whose size is large enough to matter. Sometimes the meaningful conclusion will be that the result is extremely small and/or too small to matter. The criterion amount of evidence, of course, is going to differ by the field, the context of study. Again, what criterion to use is a matter of good judgment by the scientists. We always want results, almost always want results to generalize, not to be specific to a given setting. If we have a result that only holds in one exact setting in one laboratory, that may be valid, but it may not be of much scientific import. I'll give one personal anecdote. Two of my postdocs tried many times, but could not replicate an effect published by a senior, very good scientist who concerned embodiment of cognition. At one point, having obtained positions in a Netherlands university, they flew to the U.S. and visited the laboratory of the senior scientist. They carried out the study matching as exactly as possible the senior scientist's procedures. They found they could indeed replicate the finding, but they discovered the effect occurred only if one used the exact wording of the instructions to the subjects. They had changed one word or two in their varied attempts at replication, thinking they were giving the same instructions. So the published effect was real, but it was surely too dependent on the exact context of the study environment, and therefore wouldn't really have been worth pursuing with further investigation. Of course, they stopped that line of research. Okay, none of what I've been saying provides a justification for a poor practice of science, and there are many unjustifiable factors that lead to the publication of non-reproducible results. So some are a bias to withhold publication unless a statistical criterion for existence of an effect is satisfied, publication bias, or an incentive structure that requires many publications for career advancement or provides monetary rewards for particular results. And there's usually a bias to publish positive results that are results the researcher prefers or results that confirm the researcher's beliefs. There's a bias, almost always unconscious, to design studies and to analyze results in a way that confirms one's beliefs or preferences. There's a tendency to find as more important and interesting results that are novel and unlikely. There's an otherwise praiseworthy motivation to report results that have the potential to help society. This plays a large role in health research quite often. And there's a motivation, perhaps not quite as praiseworthy, to report results that have the potential for translation into profits. The tendency for journals to publish short reports and novel and unlikely findings is another cause of some tendency for non-reproducible results. Okay, it seems obvious that remedies to current practice of science should be aimed at such sources of error and invalidity. But this approach is far harder to implement when one desires remedies than one might imagine, especially if we want the remedy to do more good than harm. Okay, so there are many remedies that encourage the collection of more data. All of these do it. We can demand a higher statistical criterion for effect size and power. We can demand a study be replicated at least once. That's another form of demanding more data. We can pre-register a study that has already been fine-tuned, publishing the results however they come out. Are these kind of remedies universally applicable or at least useful? Well, they certainly can be useful in the case of biomedical, translational, and clinical studies. We've heard a lot of cases being made for registration. The case is far less strong in exploratory research. If one adds a rule that a pre-registered study should be published, whatever the outcome, that adds some trust in the report and facilitates the publication of negative findings. Good judgment is still required. The scientists and reviewers might not notice some flaw until alerted by the negative result. Aside from correcting earlier reports, it might be that establishing that an effect is small or non-existent can be important for theoretical or other reasons. Pre-registration for this purpose could be useful. But such publications, correcting earlier reports, should be encouraged generally and don't necessarily require pre-registration to make it happen. We have to have editors and reviewers be willing to publish no results when they correct earlier findings. Let's see. To pursue this point a little further, pre-registration can be particularly useful when a researcher is trying to correct a previously misleading publication. It could help a well-done non-replication get published. And they're critically important if science is to be self-correcting. But correcting previously invalid reports is something we should encourage generally. It's not necessary that we demand pre-registration to do this. We have to have the culture of science such that we're willing to publish and correct previously invalid results. Okay. And of course, in the process of doing the pre-registration process, usually there's a review of the registered report somewhere along the way. And of course, there are problems with that if the original authors are the ones who are doing the reviewing, because many pre-registered reports wouldn't survive such a review process. Of course, there are ways around that if we're careful, but you have to do it right. Okay. The idea of having good editorial policies and good editors is important. I've run into this myself many years ago. When I was editor, I adopted the following policy. I always sent the submission, the correction, to the original authors for review, because they almost always they gave the submission the most careful scrutiny possible, looking for errors and so on. They would uncover any problems because they were motivated to do so. But I ignored any evaluation or recommendation concerning publication from those authors, knowing they'd be negative. Everyone wants to, protect their own publications. So I based the decision on my own reading and the comments of the supposedly other neutral reviewers, and as a result, I hoped that the bias that would be introduced by the reviews by the original authors would be overcome. Okay. Pre-registration obviously should not be used during the stages when a study is being tuned to operate well. There's many reasons in exploratory science why pre-registration wouldn't be a good idea. A lack of omniscience. We're all guided by the results of our studies. If we knew what would happen in advance, we wouldn't need experiments. Once we see the results, we think more deeply and see what was done wrong, what should have been done, and how to do better. Publishing what we now see to be badly flawed would be ludicrous. Okay? Another problem, there are impossible demands for reviewers. There's an immense difficulty at present getting competent reviewing for the almost uncountable number of publications. Doubling the workload through a general process of pre-registration would be impossible. And at best, the quality of reviews of pre-registered studies would be terrible. And of course, the other problem, let me go back if I can, adding noise to the literature. There are many more ways for a study to go wrong than right. A null finding can occasionally be useful and informative, but on average, most null findings would instead be due to mistakes, bad design, wrong analyses, equipment failure, and all the other ways many things can go wrong. Scientists now have a Herculean task deciding what in the voluminous literature deserves attention. Adding a host of null findings to the potential set of studies requiring attention would hardly help matters, especially when many of those findings perhaps wouldn't be meaningful. So you have to use publication of null findings pre-registration selectively, not generally, when you're doing exploratory science. Of course, one could argue that pre-registration is useful because it makes the lay public believe scientists are just doing something to deal with the problem. That may be the case, but that may not be the optimal way to foster scientific progress. The resources devoted to further assessment of a single effect can be better devoted to additional studies exploring the implications of the initial finding. Such new studies often will contain an implicit or explicit verification of the initial result, but we generally want in science to move forward, not simply repeat old stuff over and over. Okay. I want to talk a little bit about adversarial studies. Researchers with opposing views, theories, or results get together and plan all aspects of a critical study together, agreeing to live with and publish the results, whatever the outcome is. That's probably a step up from pre-registration because at least it enforces highly motivated thinking and planning in advance. But nonetheless, it suffers from the same problems. I know of one such adversarial study that was rather interesting that clearly supported one side. The loser refused to accept the outcome. Once the results became known, the loser thought of several new experimental conditions and changes to the existing conditions that should have been included. Well, maybe the loser was correct. One scientist isn't omniscient, or one team, but neither are two. I already mentioned this business about adding power to studies. Although I've been discussing the reproducibility of single effects, I want to repeat that the goals of scientific progress and understanding what's going on are not usually best met by adding power to some one effect. We learn most by not adding more and more observations about one thing, but by distributing those observations across a related network of conditions, even when one condition might have too little data if considered in isolation. This kind of approach places more emphasis upon discovery and upon patterns of effects rather than validity of single effects. This is quite different than in the case of translating a clinical problem into some kind of treatment, where knowing the validity of one effect is critical. It also, this generalization approach is important. It places more emphasis on generalization of findings than existence of an effect in some one setting. Publication bias. We've heard a lot about publication bias. And there's a suggestion one solution is to publish no results. Well, of course, in exploratory science, this is not generally a good idea. There's an infinite number of uninteresting and uninformative no results. It would add far too much noise to the literature to publish any large number of no results. But supposing some no result is likely to be informative, not in the case of correcting a previous error, but just because the researcher has reasons to believe it will lead to scientific progress. Well, whether to pursue such a no result and eventually publish it requires good judgment and perhaps more data than when a strong finding is published. A strong finding is typically outside the range of noise in the data process and is likely to survive changes in experimental setting and parameter changes, and hence will generalize. A null finding generally lies in the center of the distribution of experimental noise and is less likely to generalize and hence requires more study and more conditions. And so when to pursue null findings requires good scientific judgment. It's not a trivial matter. And this is a counter to the argument we should always be stopping publication bias by simply publishing null results. We can argue that a good way to foster scientific progress is to change the incentive structure. The current incentive structure tends to reward publishing many articles. This is especially important for young scientists hoping to get jobs. These incentives tend to cause publishing at early stages of investigation and at stages prior to additional studies that may better confirm the validity of findings. And in addition, many journals do prefer short reports, and that facilitates the tendency to publish before validity is well established. So it has been proposed that the incentive structure be changed, for example, by judging a scientist by a small number of best publications rather than by some assessment using total output. Well, there's some problems with this remedy. An expert reviewer almost always knows the scientist's total output, making it hard to ignore that information when making judgments. But even more important, productivity is a desirable characteristic in any profession, including science, reflecting motivation, writing ability, and many other factors that are desirable. Thus, productivity level really shouldn't be ignored when making assessments. So it's not so easy to figure out the right way to change the incentive structure in science that'll produce the outcomes we want. Changing journal policies. There are many journals, too many journals perhaps, publishing too many articles that are too short, with too little power and too little relevant information, with too much emphasis upon novel and unlikely results based on assessments by too few competent reviewers. There are ongoing efforts to improve journal policies, especially in the best journals, and these should be applauded. Well, there are a few policy changes I'd like to see especially. I'd like to see much less emphasis upon unlikely results. Scientific progress often occurs upon discovery of unlikely results, but such results are unlikely. That means they shouldn't be occupying the majority of publications. Scientists obtaining a novel and unlikely result should not rush to publication, but rather use extra care in exploring the result, using additional studies, additional data, additional conditions, and other means to justify and increase trust in the existence of the finding. And journals need to demand such verification when a result is unlikely. I think it also would help matters if journals, do I have any time left? Yeah, I guess I do. I believe it would also help matters if journals placed a little less emphasis upon short reports. Short reports do make it easier for scientists to explore the ever-increasing number of relevant publications. But unless backed up by other conditions and studies, decrease reproducibility. If the short report is going to be followed, and generally I like the idea, I would instead encourage long reports with many conditions and studies, but with a publication consisting of a short report akin to an executive summary, giving the summary and the rest of the main results, with the rest of the report made available as an easy-to-download supplement of some sort. Ideally, if this could be made to work, you might have the reviewers review the long version of the report. And once it's ready for publication, have the authors condense it into a short report in the supplement, have the same reviewers review the reduction for the accuracy of representing the contents of the long report. Whether the extra work involved in doing that would be worth it, I don't know, but I think that would be a good way to go. Okay, there are other ways to go forward. Open science and full reporting, we've heard a lot about that. Now, open science is a great idea. Obviously, there are many things that should be reported, otherwise we can't verify the existence of valid findings. Some things should always be reported in detail and in a manner that's accessible to other investigators. But even this rule can require exception. Of course, we know that. For example, there's rules, health rules, and person privacy rules that exist in the legal arena that prevent us from publishing all the factors that we probably ideally would like to publish if we were just interested in scientific progress. Let me catch up with where I am in my notes here. I'd say that beyond the cases where there's legal reasons why we can't publish everything, there's a lot of regions or decisions needed about what really should be reported when we're trying to report everything that we would like to report for scientific progress. The problem is that there's almost an infinite number of things that can be measured and reported. And in my own work, well, just to give some examples, let's say a physicist or chemist might not decide to report the local magnetic field fluctuations occurring during a study, or the altitude at which the study is carried out in number of feet above sea level, even though these things might matter. The scientist hopes that the findings they're talking about generalize across such variations. I don't report the time of day, typically. I don't report the time of day at which I run my human subjects, even though we know that matters. I hope the results will generalize across that factor. Of course, time of day would be easy to measure and report, but other things aren't so easy. I should report the illumination level in the room and the reflectance on the monitor I'm using to do the study. That requires expensive equipment and a lot of time and effort. It may not be worth it. So there's always a myriad number of factors that one could measure and report, but for various reasons one wouldn't want to do so. We want results to generalize across a lot of these factors, and there's a lot of decisions that have to be made about what should be reported. So it's not so trivial. There's some things that we should always report, obviously, but not everything. Okay, so remedies meant to reduce non-reproducible findings, or as we say, irreproducible findings, need to be balanced against many factors, and some of these factors are the amount of work a remedy requires, the cost of collecting data, the loss of valuable findings, too large a focus on single effects, slowing progress, reducing generalizability, reducing guidance from the data, adding more noise to the literature, increasing the reviewing burden, and other such factors. All of these things have to be balanced. A good scientist has to balance the desire to obtain more data and produce reproducible findings against many of these factors, so it's a non-trivial process to make these decisions. Bottom line is that science is actually doing quite well. In fact, too well almost. We're producing new important results at an ever-accelerating rate. But of course, we should improve its practice and reduce the number of publications of invalid or meaningful results to the extent we can by good practice. And we're doing so. We've heard a lot of this during this meeting. And we have to be careful. We have to use measured remedies to fix things. We don't want our good intentions to reduce scientific progress, which is always a danger. All right, thank you.